All right, hey everybody, welcome to the first of the 4 or 5 sessions we're going to have to help push people through the GMDSI notebook series. So these aren't designed to be your standard sort of workshop where you're going to listen to us talk and give presentations. And in fact, we decided to make the bold move of not having any presentations or slides, at least for today, to make sure we give the point across that this is not you listening to us talk. This is supposed to be us just providing you some motivation and some support to go forth and learn by going through these notebooks. So someone was asking when we're going to meet. I reckon it'll be on Fridays at about this time for the next 4 or 5 weeks, but we'll send out some definitive calendar invites in the next day or so. And so for each one of these sessions, the idea is that we'll get together, we'll review what we did last week, we'll have a discussion about that, and that'll be the meat of each of these sessions. So the idea is that we have a discussion, bring your questions, bring the things you didn't understand, bring what wasn't clear, and we'll talk about that as a group, because if you had an issue, it's likely other people probably also had the issues. And then we will have a short intro, maybe a presentation on the theoretical underpinnings of the next week's notebooks to go forward. And then that's going to be it each one of these weeks. So we would encourage you not to try to do any of the exercises while we're in these sessions. Save that for when you can sort of focus and devote your attention just to the notebooks themselves. So bring your questions, bring your discussions to these sessions, and then save the actual doing of the work for when we're not all here together. Does that sound good to everybody? Rui, Briak, anything to add on that? Good to go? Okay.
I think we could just say that we've, like, just because of numbers, we've everyone will notice they're on mute, but if you raise your hands, one of us has the power to give you a voice.
Yeah, good call. Right. Okay.
So we can have discussion. I think this week's probably less likely to be discussional, but the next couple of weeks, as people start playing with notebooks, then we might need to be a bit more discussion.
Yeah, right on.
And feel free to pop stuff into chat if you want. And just a reminder that the GitHub discussion forum is probably the ideal place if you come up with another question outside of the session and you just want a record of it.
Yeah, that's a good point, Rui. So if during the week you get stuck and you have a problem, you can, if you're very brave and extroverted, go onto GitHub and either, if it seems like something's broken, open an issue, or if you just have a question about what's happening, open a discussion. And then there's a record for anybody forever to go forward and find that issue you had and read about it and sort of get and see how the discussion went. Or if you're just completely lost and you're really stuck and you don't feel like doing that, you can email Briak, Rui, or myself, or some combination of us during the week, and we can also maybe get on a separate little Teams thing to try to get you sorted out if you get stuck. So when you're working through these notebooks, right, they are fully worked. So in theory, you could just push Shift Enter or Shift Return, as Briak says, and just blast through the notebook and watch everything happen. But that's not really learning. So the idea we were hoping is that you would, execute a code block, try to understand what it's doing, maybe go into your file system, see what files were created, maybe do a little experiment by changing a code block a little bit and making sure you build that understanding of what's happening with each one of these little pieces of code that we've written in these notebooks. And so during the class, we will go through the part 2 notebooks, which are the sort of the highest level, what we would call workflow notebooks, where they're interdependent with one another and they march through a sequence of analyses. But there's also the underlying part 1 and intro notebooks that have more granular and independent pieces of learning about the topics that are sort of woven into these higher level part 2 notebooks. So it wouldn't be unexpected of you to want to go back and look at the intro notebooks or the part 1 notebooks while you're going through the part 2 notebooks each week. And so just to show you what I mean by all that, so I'm not just talking abstractly, I'm going to share my screen. And so if you go to GitHub GMDSI notebooks and you go into tutorials, is that big enough? Can you guys see that all right? So here's where all these notebooks are laid out. So part 0, because we all start counting at 0, because that's what happens in computer science. So we have the part 0 intro notebooks. Those are sort of those are the lowest level fundamental concept type things. And then you build up a little bit into the part 1 notebooks. Each one of these is independent and covers a sort of a snippet of what would be a larger analysis you would do with a model. And then The part 2 notebooks is where things get pretty exciting, right? Where you actually go from setting up the interface, setting obs and weights, doing prior Monte Carlo and interpreting those results, running the Gauss-Levenberg Marquardt algorithm, doing first order, second moment types of things in data worth, and then IES and DA and opt and MOU. So we're going to hit most of these over the next 4 or 5 weeks. But as you're working through these, you might want to jump back and look at something about pilot points or understanding the response surface of the Gauss-Levenberg Marquardt algorithm, or trial and error calibration, or setting up the pest interface. All those things are baked in here in more detail and in more of a granular type of topic if you go back to part 1. Does that sound good? So that's the notebook structure. And Briak and I were going to do, so Tariq was asking a question in the discussions, and so he's going to get immediate feedback, and we're going to do a demo of how to use Git and GitHub live on the air. So we're doing live demos. Those are always dangerous. It may not work exactly right, but I think that's important for you guys to see that, you know, it's not all gumdrops and lollipops, as we all, you know, there's always going to be problems you have to solve and issues. So you're going to get to see us maybe debug some issues live on air, which should be pretty exciting. Okay. So Briak, did you make that repository?
Yeah, shall I just start with a little show of what
sure.
we've got with the repo, and then I'll push.
Yeah, that'll work.
Okay, so we wanted this to look a little bit like how a modeling project might look in terms of a Git repo, but then also at the same time show you how we might collaborate on a particular project. So just before 5 minutes before this meeting, I created a new repository, which isn't here at the moment. It'll be in here, called Cuddly Robot, which is a nice name that Git recommended for me. And on my computer, I've cloned that using Git clone. So Git will give you the clone address, which you can use to Git clone, and essentially it's just an empty repository at the moment. So on my system, we've got that Cuddly Robot directory, which is the clone of the repo, the empty repo that's online, and into that I've copied the Freiberg model, example model from the notebooks. So if we go into Cuddly Robot, we will see the forward model and all the files associated with that. But at the moment, the repo is initialized, but it's empty. So our log, if I spell correctly, that's not the one I wanted. I need to go into the repo first. Cuddly Robot. Then we can have a look at the log, maybe. Okay, so we don't have any commits yet, so I'm going to go ahead and add those models, those model files. Git add the forward model, and then we can view the status of this, and all of these new files have been added to the repo. So we just need to commit those changes now. Commit, and I'll just say initial forward model files added, something like that. Cool. So now we've got a git log and we've got a local commit. So all of these files are logged as part of this repo, but it's only local at the moment. So I'm going to just quickly push. Hopefully this will work seamlessly just with a git push. We'll find out. Maybe I'll check. Yeah, okay, so it should do. So it'll push to that remote, hopefully, on GitHub. And then if I go onto my GitHub and go into this repo, like magic, I've got all of the files for the forward model. So that our project is initialized, and now I'll let Jeremy have a play and submit a PR to it.
Yeah, so this is sort of, if we step back, I mean, I've been using Git, and I think Briak and Rui as well have been using Git for a while to manage not just scripts, but modeling projects, because it gives you that same sort of granularity that version control gives to software to your modeling projects. So you can watch all those model files. And now that Briok has added that initial set of model files to Git, any changes to any one of those files over the entire life of the project is now being tracked by Git automatically for free. And it becomes a really nice way for us to collaborate in almost real time on a modeling project. And so I'm going to share my screen now real quick. And I'll just show you guys the way that this typically goes, at least for me. So here's Briok's Cuddly Robot project. If I refresh that, we see he has some files here, that forward model. And so what I want to do is, in the GitHub world, you go over here and you click fork. And so that's a GitHub term. And what that means is I'm going to take a copy of Briok's repository, and GitHub's going to make a copy of it under my username. And so now I'm going to have a copy of Cuddly Robot. And so I think you guys can see that. You can see it's Cuddly Robot under my user handle, but it says it's forked from Briok originally. And so now I can make a clone of that. I'll go over here and copy this. Then I go to here. I go paste. Oh, git clone, paste. There we go. And so now I'm making a copy of the piece that I made. CD into Cuddly Robot. CD into the forward model. And let's say I wanted to make a very important change to everybody's favorite package, the SFR package. That would be what? Freiberg 6.s. Oh, I spelled that right too. Freiberg 6.sfr. Does it show up? There it is. SFR. Bring that down here. And we'll just change one of these seemingly unimportant numbers to the top. I'll make that, instead of e to the -4, that'll be e to the -2. So I'll save that, and I can go back over here now, git diff, and it'll say, oh, you made this little change. Well, I want to commit that change. Unimportant change. So I now made a message that said I made this unimportant change. Push version main. And so now I've pushed those changes back up to my version of the repository. Briok doesn't know I've made this unimportant change. But if I go back over here now and I refresh, I will see I'm one commit ahead. And let's go see that one commit ahead. So I made this one commit, and there you go. There's the little change it made. So there's a record of that. And so if I think that change is actually kind of important, I can tell Briok, hey, I want you to take these changes and use them in your version of the model files. And in the GitHub world, that's called a pull request. And so I'm basically saying, hey, Briok, I request that you pull in the changes that I made into yours. And so Git is telling me, hey, you're good to go if you want to merge from your Cuddly Robot main branch into Briok's with this one change. So I can create a pull request. Seems valuable. Put a little message in there. ... Create pull request. And so now I've swapped back over to Briok's version of the repo, and it says, hey, you've opened a pull request here. And then it's up to Briok now to decide if my unimportant change that seemed valuable is something he is interested in accepting into his version of the model files, or if he thinks I've completely messed up and he doesn't want those. And he can choose now if he thinks those are valuable. And so this is kind of how we also work with the GMDSI notebooks, that we all have our own forks of the notebooks, and we work independently until we like the way things are looking, and then we open a pull request under the GMDSI organization to bring those changes into the main repository. Does that look good to everybody? Any questions? I don't see any hands up, so this must just be easy stuff for everybody to follow along with.
I'll just point out that if that was very fast, this is being recorded. You can always go back and rewatch things at a slower rate, if that helps.
Correct. Okay, so a few important points on the GitHub thing. There is a maximum file size for any individual file that you could use on GitHub, and I think is it 100 megabytes? Is that what it is? It's 100 megabytes. So that doesn't sound big, But if you're in the ModFlow world, you can go through and write all those files as external formats. So all the recharge arrays are in separate files. And for me, usually I can squeeze in just under that 100 megabyte limit if I go into external file format. If not, there's some other tricks you can use to manage those bigger files a little bit better. And this is just my personal preference. Those Git GUIs that are out there, like lots of other GUIs, they seem very easy to use and they're making a lot of assumptions for you under the hood. I've been burned severely by these Git GUIs before, where they have some default settings of that if something's different between my version and the version that somebody else had, just accept my changes automatically without telling anybody. And that ended up setting us back several weeks in a certain project, because every time some individual on the team pulled down the changes and he had done something else, it wiped away all of our changes and just accepted his blatantly across everything. And so it took us a little while to figure that out. So just beware of those Git GUIs and make sure you understand the default settings in those. Okay, the dependency management. So there's one other thing we've done with these notebooks, and we've tried to go and be very tight about how we're dealing with the dependencies on ModFlow 6, on the PES++ tools, and also on PyMu and FlowPy. And that's because all of those tools are changing somewhat rapidly or frequently, and you can get yourself quickly into trouble if somebody's using a different version of one of those than what you're using. You'll start getting these weird results. You don't understand who's running what where. So we've tried to be very explicit about how we're managing the dependencies in these GMDSI notebooks. And so I was just quickly going to show how we're trying to do that. So if we go back into the tutorials directory, oh, actually it's up one, isn't it? Up one. You'll see there was a bin new. And inside of bin new, we've got the 3 major operating systems, and we've got the precompiled binaries for the things we're going to use in the class. And so we've gone through some trouble in the notebooks that anytime a notebook starts, we make sure that we copy in, using the operating system you're running on, these binaries into the working directory so that we have a tight control over those. And we're also using a tight control over both PyMu and FlowPy. So we also copy these into the current working space. So then Python, when you import FlowPy or import PyMu, it's pulling in this version. And we've done that, I think, most recently using pip with a cool trick that Briak showed me, where you can actually, when you create your environment, it just installs those dependent versions into your Python environment for you. So you don't have to copy those around anymore. Does that sound good? Any comments on that, Briak or Rui?
It's probably worth saying that this isn't just for the tutorials. We work like this in the real world as well, just because Python versions change and things like that. So we try and keep our modeling projects independent and reproducible, regardless of changes that happen to pandas, for example, as Briak will be happy to tell you about.
Yes, correct. Awesome. Thanks, Rui. Okay, so I think I'm going to now open up a notebook, and we're going to just quickly talk about the Freiberg model. Tutorials.
There are a few questions popping up in the chat. I don't know if you guys want to get to them now or later on.
Okay. Should we take a question or two now?
Well, so Juan is asking about guides on how to use Git. Personally, I learned from you and Stack Overflow, so I'm not a good person to give advice there. Do you guys know or have any suggestions?
I was trying to think of a definitive guide, and I wouldn't say I have one that I go to by default, but I think there's a few good cheat sheets for like the commands you'll use most often on GitHub. I think there's one on GitHub. There's probably one on GitLab as well. I mean, we should say that GitHub's not the only solution for your remote repo. There's a few other options there as well. And they all have a little bit of a cheat sheet which gives the commands you'll use most often and a little bit of info about them. So I think they're a good place to start.
And I think Mike Feenan has
put in something in there as well.
Mike Feenan has this XKCD cartoon about using Git, and it talks about all these options you can have, but really there's like 4 of them. And then there's the nuclear option of like delete everything you had and clone it again if things get too bad. And so that's how I typically do it. There's 4 or 5 commands, and then if things get completely off the rails, I just nuke the repository on my local machine and clone it fresh and start again. That's, at least for me, that seems to work. Sweet. All right, I'm going to open up one of the notebooks real quick. So again, don't feel like you have to follow along here. Like Rui said, it's being recorded. I'm just going to demo this, and you guys can then run it yourselves later if you want to re-see it all again. So I'm going to open up the intro to the Freiberg model first. So we're using this model in the class called the Freiberg model. It was originally from this guy, David Freiberg at Stanford. And he wrote a paper about it. And I first heard about it from Randy Hunt, and because Randy pointed out that this was one of the first papers to show sort of the dangers of overfitting in the presence of model error. And so what this guy did, he was teaching a grad class on groundwater modeling, and he made this synthetic model, and he gave the structure to the students, and he gave the students some groundwater level observations, but he didn't tell them what he was going to use the model in a predictive capacity for. And so the students sort of paired up, I think, and they went through and did whatever type of history matching they could. Some of them drew little zones around each water level target and got like a really good fit. Some of them struggled to find any kind of fit at all. And some of them sort of found that middle ground of maybe big zones of things. And then he compared the calibration root mean squared error to the prediction root mean squared error. And his prediction was, Mike would say this was sort of patterned after Southern California, where they were lining all the rivers with concrete at this time. And so the prediction was, what happens if we turn the river off? How much of the water level is going to change as a result of lining this river that used to exist as a natural discharge point? And so what he showed is more or less that there is sort of a sweet spot in terms of assimilating the information in the water levels. The students that did the point calibration actually had a worse fit, or had a worse predictive capacity than the students that sort of had that middle ground of fitting them a little bit. And so I thought that was a pretty cool experiment. And then Mike and Randy resurrected this thing years ago now. And then we also used it for the PEST++ version, the latest PEST++ USGS report. And so what we did there is we took the model and we made it a little bit more modern. We moved it into ModFlow 6. We changed the river to SFR. We made it transient now, so there's a steady state initial period, and there's 24 monthly stress periods after that. And during that monthly cycle, the water levels go up and down, and the river and the SFR fluxes change in space. So I'm just going to quickly run this notebook. It works. And so here's just some file manipulation things. We're going to load up that simulation with FlowPy and run it one time. It worked. There's our 25 stress periods. So we'll just quickly look at the model. It's a single layer model, 40 rows, 20 columns, so it's very realistic. And so you can see this is the standard rectangular shape of the Freiberg model. We have a no flow zone here. We have some no flow zones at the bottom. We have GHB outlet for groundwater levels to flow out of the domain as in a down gradient kind of flow. And then we have our SFR system here, this long, linear, recognizable SFR system with an outflow down here at the bottom, and we have some pumping wells. So there's 3 ways for water to leave the model domain. So it sets up a nice competition in terms of the inverse problem of where water might be going. We're using just a standard uniform hydraulic conductivity to begin with. Here's the model top and the model bottom. So you can see the highest elevation is back behind that no flow zone. So we set up this groundwater divide where water can go north or go south. And if it goes north, it probably makes it to the SFR system. If it goes south, it now has to compete with the wells and the down gradient outflows. So the way this thing is discretized in time, we have our initial steady state stress period to get the water levels kind of in equilibrium. Then we have a year of monthly stress periods, and we use that for history matching. So we're going to observe groundwater levels and surface water discharges out of the model during the first 12 stress periods. And then we're going to make some predictions over the next 12 stress periods where things have gotten drier, but we haven't observed those conditions. So what have we observed that we're going to use for history matching? We have some surface water discharges, and we have point groundwater levels at a few places in the model domain. Blah, blah. There we go. Got to a plot finally. So This fancy looking blue thing, that's our observed surface water discharge. It was actually generated with a high resolution version of this model with more rows, columns, layers, and daily stress periods. So we run that model with random parameters, and we assume that's the truth model. And from that, we take surface water discharge and groundwater levels, and then we sort of pretend we don't have that. And now those become our observations that we're going to try to match this coarse model to. So we're trying to sort of capture the essence of what it's like to use a naturally imperfect model for decision support. And so you can see our naturally imperfect model is this orange line. So it has some of the characteristics, but it's a little bit out of phase and it's going down faster than what was observed with the truth model. And then here's some plots of our groundwater levels. So we have these two groundwater series. I don't know about you guys, but this is kind of how things look when I first start running a model. It's like, oh, well, the characteristics aren't terrible, but there's some consistent offset, right? That's life, I guess, with groundwater modeling. All right. So there's our head field from the last stress period. And now let's talk about the forecast. So we're going to make a range of forecasts with this model. And we're going to carry these forecasts through all of these part 2 workflow analyses. So one of the forecasts we want to make is let me go back up here so I can see the surface water network. What is the surface water groundwater exchange in the upper half of these SFR reaches during that unseen dry period of the second year of simulation? So how much water is exchanging between groundwater and surface water up here? We call these the headwaters. And then the same, we call these the tailwaters. So how much water is exchanging down here? We want to know something about the water level, groundwater, the simulated groundwater level, an unseen location. I believe it's back up here somewhere. You guys remember where that unseen location is? I'd have to look at it. And then we're also going to do a little bit of particle tracking, because particle tracking ends up being a really difficult type of prediction to do. So we're going to release a particle up here, and we're going to measure its travel time until it makes it to some boundary condition, whether it's the well or SFR, or if it goes north into SFR, or if it makes it to GHB. So we have this particle travel time prediction as well. So we have those 4 predictions, and we're going to carry those through all of these part 2 analyses that we're going to do. Anything else? I think that's it on the Freiberg model. Yep. So we'll call that good on Freiberg. Like I said, you can rerun this notebook and read all of this great information that people have added to this notebook over the years. And now we're going to do an intro to Bayes notebook because I think it's kind of fun. Whoops.
That was Freiberg in 6 minutes.
Freiberg in 6 minutes. That's all you need to know.
That's good, man.
Yeah. Okay, so the other thing we're going to use a lot in these notebooks is some form of Bayes equation. And so there's readings you can do on Bayes equation. There's another notebook where Mike goes through some calculations about whether or not his partner watered his plant when he was out of town, and he uses that to decide if he should blame her for having a dead plant. I'll let you guys read through that one. That one's always fun. But here we're just going to use a very simple closed form solution to Bayes equation. So the components of Bayes equation are the prior, the likelihood, and you combine those two and you get a posterior. Now we're going to use it in a continuous sense, and we typically use it for parameters. And so let's assume we have just one parameter that we're looking at, and things are Gaussian and linear here. So we have our prior. Our prior is defined by our expert knowledge before we've even started modeling. So this is maybe a property of some type, and we're going to say, well, this property, maybe it's in log space here, has a good initial value of say 10, and it could be this low or this high. And then through history matching, by comparing the model outputs to the observations, those observations are saying, actually, the true value of this model, or a better fit for this model, seems to be maybe 25, because that's where the residuals are minimized. In the inverse of the objective function is the likelihood function. So that's maximum likelihood. And then in Bayes' equation, we combine these two distributions to come up with this blue distribution. And we call that the posterior. So taking our expert knowledge, combining it with the information in the observations, we now have an updated understanding of where we think the best value for this parameter lies. And it's somewhere centered around, say, 21, and it ranges down to 11 and up to, say, 40. But let's make this interactive because that's a lot more fun. So we can actually take this thing, see if I can turn off some of these to get a little bit more real estate. Yeah, there we go. So now we can do slider bars for the mean moments. I'm sorry, for the prior moments and the likelihood moments. So some fun experiments that I think are fun anyways. We can start changing the mean of the prior, and maybe we can also make the prior less uncertain. And we can start to see what happens when we start to maybe push these things apart. Like here's one that I like to do. Yeah. That's a fun one. So if the prior and the likelihood, they have the same variance, right? They're the same height and the same width. But if they're completely disjointed, Bayes' equation has no problem saying, oh, the posterior is right in the middle between the two. But I think statistically, this is a problem for us because if this was expert knowledge that said, I'm pretty sure the parameter value is over here, and the data are telling us, no, that's actually way over here, I think in statistics, they call this surprise. And it's okay to get surprised once in a while, but if you're getting surprised consistently, maybe that's an indicator that either something's wrong with your likelihood function or something's wrong with your prior. So this is, we call this prior data conflict, and it's something that I've been a little bit obsessed about lately. But more often than not, this is the kind of situation we'll see, I think, or we hope to see. Maybe it's not quite so bad. That the prior will be quite diffuse, right? We don't have a lot of great understanding for any one model cell what the hydraulic conductivity would be, but through data assimilation, we're getting a much stronger and updated understanding of where we think this true parameter value will lie. And so this means we're learning a lot from the data, and we're not learning a lot from our expert knowledge. Anyway, there's a range of experiments you can try down here and some questions to sort of check your understanding. I would encourage you guys to go through this Bayes notebook and have a play with it. Anything else, Briak and Rui?
I think that's good.
Cool. Okay, so those are the two intro notebooks, and I think we're going to let Rui now talk about the PEST interface. Unless we have any questions we want to take at this point.
Let's share my screen. There we go. Let me know if that's too small to be seen. Okay, so you all thought you were going to be learning about Python, but we're jumping a lot into the nuts and bolts before we actually move into that. I mean, if we think of PyEmu or even any of your custom Python code or scripted other languages that you might be using, effectively, all of these things are still glorified GUIs, right? We have a lot more control, we have a lot more customization, but at the end of the day, they are interfaces that are dealing with managing PEST and setting up PEST workflows and so on. So I don't know about you guys, but I never have a case in which something doesn't go wrong. And when something goes wrong, you need to be able to go down into the nuts and bolts and be able to figure out the plumbing of PEST and figure out the plumbing of all of the file structures and so on, and figure out where the problems are, troubleshoot. So for some of you, this might be old news, but just so that everyone's on the same page, we're going to go quickly through what the PEST interface is and some of the key components of it. So when we talk about the PEST interface, we're talking about essentially the set of files which are required to run PEST in terms of instructing PEST on what it is that we want it to do, as well as how PEST should communicate with the model that we're trying to work with. So there's three main components. If I can scroll down here somewhere to find them. When we're talking about a PEST interface. So there's the PEST control file, which has all of the instructions for how to run PEST and what PEST should be doing. Then we have template files, which are files which tell PEST how it should provide information to our model, whatever that model may be. And then we have instruction files, which are the files which tell PEST how to read outputs from the groundwater model. And you may notice that all of this doesn't require that PEST actually interfaces directly with whatever we call the model. This is what we mean by PEST being non-intrusive. It doesn't need to communicate directly with whatever the modeling software is that we're using. It just needs to be able to read and write ASCII-based files, which our modeling software is able to read and write as well. So this means that we can use a arbitrarily complex model. Doesn't really matter what software we're using, as long as there is, or that software is able to read ASCII files, write ASCII files, and be run from the command line. So that's the third piece that I forgot to mention, is that, sorry, where did I go? Lost myself. Not up here. Down here, there we go. Is that we need to tell PEST how it should actually run the model. So when I say the model, I don't necessarily just mean a modeling code like modflow or feeflow or something like that. It can be anything that can be run from the command line. More often than not, this means a whole mixture of pre-processors, post-processors, potentially multiple different groundwater flow models or transport models or whatever type of models, all of which become part of our forward run or our model. So when we're talking about the model, we're talking about that whole package and not simply running modflow. And this means that whoever is setting up, or a user that's setting up a PEST interface has lots of flexibility as how you can design a model's parameterization scheme, how you pre or post-processed inputs or outputs from that model, as well as calculate like secondary types of observations and so on. So sky's the limit. I mean, and again, if you're relying on a GUI, a lot of this stuff will be quite limited by what the GUI can do. The major advantage, in my view, of working in the scripted workflow is that you have the control and the ability to customize these things to a level of detail which is usually required for the types of complex analyses that we do, which are never standard, right? So every time we do a project, it's different. Quick view of what a control file looks like if you haven't seen one. So let me know if Jeremy, is this visible on my screen? I can't see. Good, okay. So this is a control file, looks really fun to look at. You can go through, this is from the tutorial folder, and so you can open it up yourselves and look at it if you're not unfamiliar with it. There's a few different sections which matter here. The first section is your control data, which has a whole bunch of variables, which I'm not going to go through. I recommend reading the PEST manual in all its glory to know what all of those things mean. The major one is an OPT max, which I can't see on my screen. Ooh, what's happening? If we scroll down here to the bottom. So this is a quick cheat sheet for what you're seeing up here. And the one you're most likely to change most frequently is NOPT max. I can't remember where it is, doesn't matter. And a few of the others which you might find occasionally or case specifically require changing. Don't touch that, it's probably good as a default. And then you'll have the sections in which you define your parameter information. You'll notice here parameter groups. Most likely than not, you're not going to be changing these unless you have a specific case. But then here is the individual parameters, each of which you'll be defining where you will be defining their initial, essentially your best guess, your initial value, and your bounds, as well as how it should be transformed. So in this case, we've only got one transformed parameter there. Just to, okay, I'll show you the template file in a second. The same happens for observations. So the second set of groupings in the control file will be your observation groups, and then your observation data, or your effectively your calibration targets, and as well as any other types of observations you may be tracking. Again, your target value and your weights and your observation groups, which are repeated up there. Yada, yada, yada. We've got lots of observations here for our Freiberg problem. And then here, the key line, which is our model. So you notice that this is not run modflow, it's actually run a batch file. And in the Python world, this would normally be a script. So you'll see in the subsequent part 2 tutorials which we have a forward run.py script, which runs our model and all of our pre and post processes as well. And then here is the key point of telling Pest how to, which are the model files that you wish it to change, and what is the structure that it should use to find where it should change each specific parameter value. And I'll just take a quick look at one of these template files. So I have here open one of the array inputs for the Freiberg model. In this case, it's just the porosity, and it's a really fun file to look at, array of 0.01s. And here is a template file in which each of those parameter values is replaced by the parameter named NE1 within this space. And so Pest knows it needs to open this file and change it with this structure and put in this parameter value into that space. And the same applies for observation files. So here we have the instruction files, which are for reading in observation data. And again, here is one of the output files that modflow6 writes. So it's a time series of the head and tail waters for the SFR package. And here's the equivalent instruction file for reading in those observations. So this is essentially a set of instructions for Pest to know, move down the line, find this indicator, this is that observation name, value will be in this space, and so on and so on. There's a whole bunch of other rules into how to design instruction template files. I highly recommend reading this thing. So hopefully you can see this, which has a lot of the description in there, as well as any of the Pest manuals, which will cover all of the little details of how to construct these things. Now, in the part 2 notebooks in which we design our Pest interfaces to build these things, you will probably not be seeing each of these steps directly. You'll be using the code to automate reading and writing them. But it's important to understand how these structures actually work for when problems happen. All right. I think that covers what I wanted to say. Anything else you guys want to add?
I was just going to add, you mentioned that we have a lot of observations, quote unquote, observation data in the pest control file, even though we only have a handful of things that we've actually observed in the past, observed from our truth model. And I think that's an important point, because in a lot of times, I would call those sort of diagnostic observations or auxiliary observations. They're quantities from the modeling process that we want to watch, that we don't necessarily have something we want to match against, but that are important to understand how these things might be behaving. And so some of those are the forecasts. So we're actually, in this model, we put the history and the forecast together into one simulation. I always try to do that in every modeling project I'm involved with, even if it's not the exact forecast that everyone's going to want to see at the end, but it's some proxy for that forecast of water balance change under a future dry condition, something to give you an idea of how this model is going to behave when you change stresses later. And then you can monitor like the ModFlow, cumulative budget information from the list file. Man, that stuff is so valuable to watch. Or just counting the number of times you see the word failed to converge in the list file. Like, just as an observation, it's just a count. How many of those do you see? If you start seeing hundreds of those, it's good to know, oh wow, these models are like failing to converge every single stress period. And you would have no idea if you're using the continue option in ModFlow that the model has gone completely off track. And so just having those sort of diagnostics, they take up a little bit of storage, but they don't cost any more model runs. And I don't see any reason not to start to include all manner of sort of anything related to model performance that you would want to watch as an observation.
Yeah, especially moving into the ensemble space. I mean, I find myself tending to err on the side of caution, tracking more things than I think I need, which sometimes puts me in trouble with storage space. But I usually find it's better to have it than not. And that was one last thing I wanted to add. So I'm showing you here a old or version 1 type of pest control file. You'll see that we use version 2s, I think, in the notebooks, in which they are a lot, well, I should say easier to read because they're structured in a more CSV friendly type of structure, I'd say. But what I wanted to mention is that whenever you see a pest control file with the plus plus or entries with these plus plus signs, these are specific to pest plus plus, and they are commands that will only work if you're using any of the pest plus plus codes. But if you're using old school vanilla pest, then it'll just ignore any of these things that are in there. Yeah, I think that sort of covers it.
And there was also a question about the compatibility with templates and instructions. So we've gone to great lengths to try to make sure that Pest++ and Pest will use the same template and instruction and control file information. So like Rui mentioned, Pest HP will skip the ++ arguments, but they should be interchangeable in terms of templates and instructions and control file format, except for maybe a few sort of more advanced things that John is adding to the top of the pest control file. Other than that, at least template and instruction wise, I'm pretty sure they're fully compatible.
I would add, except for size, the lengths of parameter and observation names.
That's right, except for that piece. Small detail.
Cool. Thanks for that, Ray. Should we try and quickly go over an example of how you get to what Rui was showing using the PyEmu methods? So if I share.
So I did Freiburg in 6 minutes. Can you PST from in 11 minutes?
We'll give it a go. All right. So while those two were yapping on, I in our cuddly robot directory, I've created a new notebook, a new empty notebook. So we're just going to like introduce some of the main components of setting up what Rui was just showing, the pest control file, using PyEmu's PST from method. And there is like a short recipe within the notebooks now that was added in the kind of last iteration of the notebooks a few months ago that gives the main components of the pest from method in a very kind of vanilla way, but hopefully it's going to work as a reasonable reference to how you get started with it. So I'm going to try and do it live, which is always a risk. So the first thing we do is probably import OS, or maybe from pathlib import path as another option. We're going to want PyEmu. That might be all we want. One thing I've done is copy the executables that I need into the model directory. So hopefully the model will run. And we'll see how that works. So, right, we import everything okay. So then the first thing I want to do actually is to run the model within that forward run directory. So I can use PyEmu's got some handy hooks for doing that. osutils.run, something like that, isn't it, Jeremy? And then I can pass mf6 to run modflow 6. So I want the folder that I'm trying to set up pest around. I want that to contain our model output, so we can set up those instruction files to look like what Rui was just showing. So I think I need to pass this DWD equals, should have called it a shorter name, forward model. This is the first test. Cool. That's probably because I didn't close the string. All right, so that's running, or run the simulation. Gee, fast models are good. So that's run the simulation inside here. So we should now have some output files that we can play with in that cuddly robot project. All right, so the next thing we do is try and set up pest from. So we might set up a little variable to be the directory name that we want pest to be set up in. And then we might initialize pest from. So pinemu.utils.est from, there he is. So there was a glimpse at PST from FlowPy there, which was a blast from the past with the predecessor. So here we will pass the folder that we want to set up. And our template directory name. And we can go ahead, I think, and initialize that in a very nice, straightforward way. So you can see straight away that first step just copies all of those model files. So it makes a carbon copy of our model directory into this template directory, and it adds these two, molt and org, which we'll come to later.
Do you want to mention something about the philosophy of why we have all of these different folders?
Why we have the multiply. So I guess we can.
No. Why the template folder is different from the model folder? And
oh yeah, so that's really just to preserve that model folder, so that we're not goofing around with the model that we know that works. So we're preserving that as our reference, and then we're building it around in a template directory where that's where we might be in danger of breaking it. So it's just to keep a bit of preservation of that model that we're happy with, that's working, and a bit of separation before we start potentially breaking things by entering the pest world with it. And then inside there we've got this these two directories, multiply or molt and org, and that's so we can use multiply parameters within PyEmu and within the PyEmu process, and we just will copy versions of our model input files to org, and versions and our actual model parameters, the multiply versions, will go into molt. You'll see that evolve as you start playing. So the next thing we need to do is, why don't we add some parameters? So for model, what parameter file is a good one to add? I could do recharge stress period. What does that file look like? Ah, yeah, that's an array type file. Okay, let's give that one a go. So pf.add parameters, and then we pass a file name that we want to parameterize, which will be Freiberg 6.rch recharge 19.txt. And we're going to say we want to parameter every model grid cell. So let's come back out and go into our template directory where we're currently working. And here we go. We've set up parameters for that model input file, and we've created a template file that looks a bit like that, but probably without the word wrapping. And then these are by default, we've set up these parameter names. So because we haven't passed much else to this add parameters method, it just gives it some default names for parameters, which might not be that informative, but it's a good starting point. And there's lots we can do, which I'm not going to get into right now, because you'll be playing with that in the notebooks. But there's a whole heap of arguments that we can pass to that method, and it gets pretty involved pretty quickly. But you can change things like the base name of the parameter group, adding things like your variogram so you can correlate those spatial parameters but we'll leave it with those ones for now. So why don't we add some observations? So pf dot add observations, and let's set those up around that SFR CSV file that Rui was showing earlier. So for this, because of the, if I can find it, there he is. Because this is like a tabular output file from Modflow 6, we need to tell PyEmu pestFrom what index and what columns to set up as observations. So we pass index cols equals time, and use cols equals, let's go with tail water, and then we can run that one. And in a similar way, we'll just get kind of quite defaulty observation names, and you can see that we've built instruction file to read those outputs from the model output file. And likewise, similar with the parameters, there's a whole range of options there for how we might get a bit more granular and a bit more detailed around pulling out those observations from those output files. So we've added parameters, we've added observations, we've got one set of instructions files, one set of template files. What we need to do now is tell PyEmu what we want to be as our forward model command. So what we actually, I need a dot append, what we actually want to run at runtime, and that's going to be mf6. So what we'll be doing is building in Python, building a Python script that will get run at runtime, and this is the model call that will get input into that Python script that gets run at runtime. So we just need to essentially just add it to this list, and then we're ready to build a pest control file, I think. pst dot PyEmu dot build pest, and let's just call it eg.pst. Probably going to want to make that a string, and if everything's, haven't missed any steps, we should see a pest control file and a forward run script. So there's the pest control file. Let me just get rid of those word wraps. So there's our parameter groups. We just added one set of parameters, just that one call to add parameters, but there's all of those granular grid-based parameters that we've added, and then just one call to add observation, so just one observation group, and then all of those observations that are in that file are added as outputs that we're tracking in the pest process. And then the forward run script that gets run at runtime is pretty simple. It's a method that gets called to apply the multipliers, those multiplier parameters, and then running Modflow 6. So we're flying through, and then we can just see whether it all hooks up. So osutils.run, and then we can hopefully pest pp-glm, and then just call that on eg.pst and pass a directory. And hopefully that'll run an nopmax version of pest, nopmax 0 version of pest. There we go.
Boom.
And that is it. Boom.
Man, go to whoa right there.
And this is, so there's a version of this, just a similar kind of similar work through within the notebook within the notebooks now, and there's a much more granular version of it that comes within those part 2 notebooks, which I think is brings us on to our homework, right, Jeremy?
That is correct. All right, so
Cool.
You made it through the first session. That was awesome, Brioc. Appreciate that. So for this week, we're going to do the very first part 2 notebook, which does what Brioc showed you there, but with a lot more steps and like more parameterization, more observations, and some more sophistication to sort of give you a flavor of how this looks at industrial strength scale and how you might apply it in problems that you're actually working on. So I'm going to share my screen and I'll show you guys. Does that show up? I share the right screen? Maybe? Is you guys seeing
the notebooks? Yep.
Oh, okay, there we go.
No, I'm seeing
the
my
notebooks.
Yeah.
Your hair. There we go. So we go down. So this week, we want you guys to work through part 2, 01 PST from PEST setup. So there's a notebook in here. And this notebook essentially does what Brioc just did, but at a much larger scale. And it does it for all different manner of inputs and all different manner of outputs. And it adds some custom functionality to the interface and sets it all up. And also steps through the multiplier parameter process a little bit too, to try to explain what's going on with that. So for next week, we would like you guys to work through this notebook. I guess we can put a link to that in the chat. How about that? Would that be useful? Copy link. Up here. And we'll put that in there. So that is the one notebook to do for next week. And so work through that, take your time, try to understand what it's doing, bring any questions, discussions, any of that stuff back with you, or alternatively open up questions on GitHub if you get stuck. Any questions or discussion about what we covered today? How's everybody feeling? Feeling good?
Comments and criticism.
Yep, send your
Positive
criticisms
only.
directly to Rui.
I was just wondering, does everyone have our email addresses?
They should. So when I sent out the invite for this meeting, all of our names were CC'd. So if you need to get in touch with us directly, you can just email us by replying all, I think. Did I lose connection?
But as Rui said at the start, the discussions within the notebook repo, really encourage people to use that if they have questions. And there's a whole load of people within this group that know a whole lot about and have a lot of experience about using some of these methods. So I think there's a reasonably broad support group already. So it's worth asking questions on the discussion, and then you're not just relying on the three of us to pontificate.
Awesome.
And it'll also allow for crossover with the Americas group. So I'm sure there'll be interesting stuff coming both ways.
Awesome. Well, I guess that's it. If there's no other questions or comments, I know Tariq had a question about prior data conflict conceptually and how that interplays with forecasts, but I'd really like to hold that until we get to a notebook that talks about prior data conflict. I think next week even, that'll be next week's assignment. We'll start to talk about prior Monte Carlo and prior data conflicts. Let's do that when we get to it. Okay, if there's no other questions or comments, we'll see you guys next week, or we'll see you on GitHub.
Oh, looks like something just popped up. The question from Kaylee. Chat keeps moving.
Question.
Can't see it.
It's a good question. He's asking about, is there a way to sort of programmatically build, like, say, a groundwater vistas file from modflow files? And I've asked Jim a few times, like, to share the format of the groundwater vistas file if it's something, because we could potentially hack something to at least build a basic one. But we'll you guys feel free to write to Jim and also ask for that. Maybe if there's enough people asking for it, it'll happen.
Yeah, the inverse would be quite useful. So many times I get a vistas file.
Right. All right.
Cool.
I guess we will catch everybody next week.
Awesome.
I'll send out an invite soon.